Welcome back, everyone. So forest fires, obviously something we hear about a lot on the news, and as usual, I think you'll find out that it's complicated, I think is the bottom line, and this time it's even more complicated than normally. So let's see, let's start from the basics.
Up and down much of the West Coast, this has been a week of fire and destruction.
And after going through such misery, it's hard to fathom that the worst may be yet to come.
Okay, that was encouraging, no question. Okay, so how about if we start by plotting the trends, and then we can discuss that after we've seen the data. So these are the Canadian forest fires. What do we see, Sarah?
It's a negative trend.
A negative trend. And here's a more complete picture of more things. So the western US, no question, is seeing a rise. We're going to analyze and attempt to attribute this to anthropogenic global warming. You see that the number of Canadian fires is going down. The area burned is sort of steady. But you get the idea that fires can be quantified by the number of fires and by the area burned. These are two different things, right? And then the global fires decrease by about 20%. And we'll talk about that too. Turns out that's dominated by Africa. It's a completely different issue, and we'll see why that happens. But I think just looking at this, you understand that it's not that fires are increasing everywhere. So what we want to understand is, where are they increasing? Is this increase related to global warming, which we'll see in some cases it is? Why could it be decreasing in a climate change scenario? Why would forest fires in some area actually decrease as opposed to increase? And hopefully we'll get a fuller picture by the end of the day. Okay, here's another useful video. All right. These are the three essential elements for fire to happen, right? You need fuel, you need something to ignite the fuel, and you want the fuel to be dry. If you have a combination of all three, then you can develop a fire, and a significant fires. And humans can introduce perturbations in any of these three. They could affect the fuel availability, they can cause ignition, as we'll see, and climate change due to human activity can also change dryness. So we can influence all three factors. And I think this slide, let me show you what it's going to look like at the end, like this, is an important one. So let's try to go slowly, element by element, and understand what's happening here. Okay, so first of all, what are the climate factors that affect fires? Okay, so look at this. If the previous rainy season precipitation was higher, then you're going to get more vegetation growth, right? Similarly, if the spring melt was earlier, you expect more vegetation growth toward the summer. Summer is when you expect more fires. And then if you have warming, droughts, dry weather, all of that can lead to drier fuels. So that's also a climate factor. And finally, stronger winds, which are also a climate factor, can accelerate both the drying and the fire spread. So these are all climate factors. Warming can lead to dryness, winds can lead to spreading and drying, and different precipitation can change the availability of fuels. Are we all okay with this list of how climate can affect fires? Okay, great. Now, there are also human influences that are not climate related. So let's see how that happens. First of all, in some areas, 95% of all ignitions are human activated. So in many populated areas, ignition is not a limiting factor. It's not about would fire start. Fire always starts. It's whether it would spread once it starts, because we're always there to start it, unfortunately. Okay, so that's ignitions. And then, of course, logging affects the density of forest, and that can affect the spread of fires. Conversion of land to and from agriculture. If you have less forest areas and more agricultural fields, then you'd have less fires, and vice versa. Fire suppression policies. So if we try to suppress fires for many years and we leave these fine fuels in the forest, where they would have burned otherwise, then we have accumulation of fuels, and that would lead to a huge fire. You hear about that a lot. So that is a significant issue. So the fire suppression and buildup of fuels. Population increase, of course, has several effects. First of all, more ignitions in the area close to the population, and then people also build in fire-prone areas, and that increases the damage. So these are all human effects that have nothing to do with climate. Emma?
Wait, can you explain again logging? Like the less dense forest makes it spread more?
Yeah, so if you cut trees as part of logging, making the trees less dense, it might affect the spread of fires in the forest.
Does it make it like more likely to spread or
I would say less. If the tree density is smaller, it might be less likely to spread around.
And I'm wondering if there's any, like with the agriculture stuff, like are you saying that the agricultural land burns easier than?
So it depends what agriculture, what crops this is, and depend what forest it was before that, right? So you could think of combinations in which switching from a natural environment to agricultural areas would increase fires, and you could think about other cases where it would decrease fires. But the point is that switching between the two changes the fire regime. That's the idea. So why is it complicated to detect the signal due to anthropogenic climate change on fires? This is everything we hear about is forests are affected by anthropogenic climate change. It's clearly an intuitive idea, but let's discuss why is it difficult to actually make an attribution in some cases. So when we thought about sea ice, hurricanes, droughts, floods, and so on, it was enough for us to see that there's a change in the regime of variability from the natural variability regime. As soon as we saw something that didn't look like natural variability, we could blame climate change, anthropogenic climate change. It's different here because we could see a change in the fire regime, but it may not be related to anthropogenic climate change. It may be related to the fact that humans are starting more fires than would have happened naturally. So the fire season that used to be limited to a certain period where you have lightnings and so on that would start fires is now extended because we have ignitions almost any time of the year, depending on the area. So detecting a trend that is different from natural variability is not, in this case, the same as detecting the effects of climate change. Is the difference clear? So we'll do an analysis of two cases. One would be showing that the forest fires in the southwest US are likely due to anthropogenic climate change, and then we'll look at Australia, we'll see that something else might have happened there. Okay, so there are additional factors. Sometimes the composition of forests change. So forests have their own dynamics, and sometimes the change in forest type, the tree type and so on, can change the fire regime, the possibility of fires spreading, because the tree type changed, the size of the trees changed, trees got older, younger, and so on, the density might have changed and so on. Also, if you have a large fire one year, then obviously the next year, there aren't going to be that many trees to burn, so a fire in 1 year affects the possibility of starting and spreading a fire the following year. So there's a history effect as well. Okay. So now the important thing to know about fires are that the fires are a natural part of the environment, right? Fires are not necessarily something that was introduced by humans. It's always been there. The plants and vegetation and ecosystems have been used to it and learned and evolved to live with it. And we'll see a wonderful example in a second. This is how we know that fire has always been around. You can look at lakes. You drill a sediment core at the bottom of the lake, and you see layers of ash that you can even date. And you can see that there was a fire pre-anthropogenic periods, for example. You can see major fires in ash layers at the bottom of lakes. You can also look at tree rings and see burning marks in tree ring data, which also tells you that fires existed in the past. So fires are an important part of the natural system. Not only are they an important part of the natural system that always occurring, some plants actually evolved to take advantage of fire. This is a good example of plants that evolved to use fire to their advantage. Basically what this shows is they put these cones in an oven and they heat them, and then at a high enough temperature, the cones open. So what would happen is other vegetation would burn due to the fire. These cones are protected, and as a result of that, these plants are able to spread and use fires in order to be able to spread, right? That's the idea here. Now that we know the basics about fire, our intention is to try and calculate to what degree are fires increasing or not increasing due to anthropogenic climate change. For that, we need to understand the climate effects on fires. And the climate effect of fires are based on these things. So there's something called the vapor pressure deficit, the climatic water deficit, and fire indices. All three concepts are used in order to relate climate to fires, typically to the area burned. So let's try to understand these things, and then you'll be able to do the analysis relating fires to climate change, okay? That's the plan. Okay, so let's see. What is VPD? So VPD is defined as the saturation water vapor pressure. So you remember Clausius-Clapeyron from different areas. This time, instead of thinking about specific humidity, that is the weight of water vapor in a kilogram of air, we're thinking about the pressure, the partial pressure of the water vapor within an air of a given pressure. So E star of T would be the saturation vapor pressure. What is the pressure of the water vapor in the air, if you want, minus the actual water vapor pressure. So this difference is defined to be the vapor pressure deficit. So of course, when the vapor pressure in the air is when the air is saturated, this would be equal to that, and this would be zero. When the air is very dry, this would be large, and therefore this would be large as well. So this can be calculated directly from Clausius-Clapeyron, as we did in the past. And this is something that you observe in the atmosphere, and the difference tells you what happens. So now, if the water vapor pressure is constant, you say it has a certain value in a certain area, and the temperature changes, this thing will grow exponentially with the temperature. So this thing grows, the VPD grows exponentially with the temperature if the atmospheric water vapor pressure is constant. Make sense? Okay. So this, again, this is exponential with T if E is constant. Now, it's even more powerful than that, because suppose that's what's constant is not the water vapor pressure, but the relative humidity. So if the relative humidity increases, if the relative humidity is constant, so if the relative humidity is constant and the temperature increases, then remember that the relative humidity, let's say that it's going to be proportional to something like E divided by E star of T. Okay? So if it is constant, it means that E must be growing exponentially together with E star. Okay, now relative humidity being constant in a global warming scenario is sort of a default assumption. So even in that case, when the relative humidity is constant and E itself growing exponentially, it turns out that the VPD still grows exponentially with temperature. Let's see why that's the case. So the VPD is equal to E star of T minus E. Okay. E in this case is equal to, so this is E star of T minus E. So E from this equation, assuming relative humidity being constant, is equal to relative humidity times E star of T. So this is equal to E star of T times 1 minus relative humidity, and that's also exponential in T. So the vapor pressure deficit, which is sort of a measure of the demand of the atmosphere for moisture, is going to be exponential in temperature. Now, the higher the VPD, the more drying of fuels would happen. So let's note that. So higher VPD implies more drying, because it means that the atmosphere is dry relative to what it could have been. You know, this is how dry or moist it is. This is how moist it could have been. The bigger the difference, the drier the atmosphere relative to what it could have been. That allows for more drying of fuels, and that allows for... So this affects the dryness element of the three criteria that we talked about. Okay. So I think we understand VPD. Did we cover everything here? Yeah. The point is that we understand that a higher VPD leads to more drying. And it turns out that there's a very strong correlation. You'll see this soon. Between VPD and area burnt. So this strong correlation between VPD and area burnt means that VPD can serve as the climate connection between forest fires and climate. So the fact that people found this strong correlation allows us to relate climate to forest fires. Now, this correlation also makes sense, as we said, because the VPD increased dryness, and we understand that dryness is one of the three important elements that lead to fires. So the next one is the evapotranspiration. This is on the way to understanding potential evapotranspiration. But evapotranspiration is simply evaporation that happens through the leaves of plants. You know, the plants draw water through their roots and evaporate them through their leaves. So you have evaporation from the soil, but you also have evaporation helped by the plants, and that's referred to as evapotranspiration. What's important for us is the potential evapotranspiration. So that is the evapotranspiration that would have happened if the surface was simply water unlimited. If the surface had plenty of water, and the only thing that determines the evaporation / evapotranspiration is the atmospheric dryness, then the evapotranspiration would have been equal to the potential evapotranspiration. Let me say that again. So the potential evapotranspiration is what the evapotranspiration would have been if there's no limit of water at the surface. Okay? Why do we care? Because the next measure is helpful in terms of fire, connection to fires. So this is the climatic water deficit. Is something else that can be correlated with the spread of fires, with the area burnt. And that is the integral over a season of the potential evapotranspiration minus the actual evapotranspiration. So if a surface is completely water covered, then its evapotranspiration is equal to the potential evapotranspiration. In that case, this climatic water deficit would just be zero. If a surface is dry, then the difference between the potential evapotranspiration and the actual evapotranspiration is large, and then this quantity would be large. So this measures, again, the ability of the atmosphere to dry fuels, and generally the dryness of climate. And that's therefore can be related to forest fires. Okay, moving on. So now we can use this to discuss fire indices. So a fire index is an index you develop to tell you what is the danger of fire today in any location. You could draw a map of the fire danger. And this is an algorithm that is used by typically government agencies to figure out what the danger of fire is. So it's typically called fire weather index or something like that. You'll see there are several different systems. So this one is the Canadian Forest Fire Weather Index. So what do we have? We have fine fuel moisture code is simply the moisture content of fine fuels. So this indicates how easy it is to start a fire, because if the fine fuels are easy to burn, then the bigger logs and so on can be ignited as well. But you have to start fire with fine material. So this tells you how easy it is to start a fire of fine material. And then same idea. So moisture code is the average moisture of loosely compacted organic layers. drought code is how dry, what is the average moisture of deeper organic layers. So, once you burn the surface, if you want the fire to penetrate deeper, you want the deeper stuff to be dry as well. There's the initial spread index, which tells you how easy is it to spread fire. That depends on the winds and so on. If the winds are strong, it's easier to spread fire. And there's a buildup index of how much fuel is available. That is a function of the history of the forest over the last weeks, months, and years possibly. And then you use all of these to calculate the fire weather index. And this is an example of such a fire index. So you see this is August 15, 2020 in Canada. You see areas with a large index and areas with a low index, and gives you an idea of where should I beware of fire and where should I direct my fire prevention and suppression efforts on a given day. Make sense? So I think what we want to do next is this: understand the vapor pressure deficit by plotting it in different ways. Let's go for that workshop. Thank you. Do you mind if we look at the following slide? So you can see here, in the assumption that the relative humidity is constant, you could see how the blue curve, where the water vapor or the specific humidity in this case grows exponentially, and the saturation moisture grows exponentially, but the difference between the two also grows exponentially. So that is what we said before: VPD grows exponentially even if the moisture in the air grows together with the temperature, assuming relative humidity. Okay. Now, just wanted to explain how impressive is what we're seeing here. So first of all, you see the area correlated, the area plotted versus the VPD, and here you see the log area versus the VPD. Now, you can clearly see that the correlation here is pretty remarkable. Did anyone calculate the R squared and so on here? You could calculate that later, but you could see how good the fit is. Now, I wanted to emphasize how super impressive this is, because think about it. Fire depends on ignition, dryness, fuel availability, human interference in all sorts of different ways. And in spite of that, there still is a very close relation between the VPD and the log 10 of the area burnt. So it's actually remarkable that in spite of the fact that, for example, ignitions are also a human effect, there is a strong climate effect on the Southwest fires that is expressed through this dependence on the VPD. If we didn't have such a strong correlation, we wouldn't be able to attribute the fires in the Southwest US or in the Western US to anthropogenic climate change. So I just wanted to emphasize again and again that this is a remarkably surprising and powerful correlation between these two quantities. Okay? So let's see how we use this remarkable correlation. The first thing we need to do is understand the difference between weather and climate. You probably know this intuitively, but let me just emphasize the fact that weather is obviously chaotic. Climate change is not necessarily chaotic. It just responds to the CO2. So let's see first of all what is chaos. So start with this one. This is a simulation of a chaotic system. Whatever the quantity is, you could see how it's oscillating here, switching to a different mode, and it never repeats itself. This could be the solution to 3 differential equations. It has to be at least 3. You solve 3 nonlinear differential equations, and you get something like this that never repeats itself. But what we see here is interesting. Now we see that there are actually 3 different solutions here. So what happened is we started at t equals 0, at time equals 0, 3 different runs of the solution to these equations. And the 3 were remarkably similar. The difference might have been 10 to the minus 10. And for a while, the 3 track each other very closely, and you don't see that there's actually 3. Then eventually, the small change in the initial conditions leads to a growth of the error, a growth of the difference between them. So you can see that by this time, by time 11 or 12, two of them separated, and by this time, 13, the third one also separated. So what's this referred to as is sensitivity to initial conditions. This is the hallmark of chaos. Chaos is, to a large degree, sensitivity to initial conditions. You start a system with very similar initial conditions, but not identical, it would eventually spread. Any questions about this one? Let's see an actual experimental system that displays chaos. So this is a double pendulum. Let's look at that. But what you could see is these oscillations are very irregular. They never repeat itself. If not for friction that eventually kills it, it would continue forever and never stop and never repeats itself. That's also remarkable, that the system can vary forever like that and never repeat itself. The water system is exactly like that. The water never repeats. Think about this. If we started this pendulum, we would move this to some degree and release it, just like this person did. And then we would do it again, but this time we would place it in a slightly different initial condition. Initially, the pendulum would behave exactly the same, but then it would deviate, okay? So now people do exactly the same with the climate model. They initialize the climate model in 1920 with a certain distribution, winds, and so on. And then they run it all the way to 2100, and then they initialize it again, the only difference being that they're adding a temperature perturbation of, say, 10 to the minus 10 at some grid points in the model, and then they run it again. So initially, the weather looks exactly the same. But after, depending how large the initial perturbation is, after a few months or maybe a bit more or less, the two systems deviate. And now you get a storm in one model run where you didn't have a storm in the other one, or you get an El Nino event in one model run that you didn't get in the other. So these are different realizations of the climate system, driven by slightly different initial conditions in an ensemble of model runs. And the only thing that now, if you have a CO2 increasing in these, then you'll have warming in all of them, but the warming would be slightly different in each of them because of these natural variability signals, the El Nino is happening at different times, and so on and so forth. So what we can do is, if we have many of these runs with different initial conditions, slightly different initial conditions, we average them together, and if one had an El Nino and one had a La Nina, they'll average out, and the net would be zero effect of El Nino, and then we can see only the signal of climate change. So here's what that looks like. So that's what you see here. You see about 30 different model runs. These are the gray or the colorful lines in the background. One of them, number 33, just by chance is highlighted in black. The black line is a typical realization of the climate system. What's shown here is the surface temperature in some place in the western US. So the black line is what a typical temperature record would look like. The observed record might look like that. But in the background, we see 30 more of those. And if we average them together, we get the red line, which you see the variability of the red line is much smaller than the variability of the black line, because now this variability is canceled out. And you're left with the red line, which is more of a climate signal as opposed to weather and natural variability signal. If we had more ensemble members, then the red line would have no fluctuations or much less fluctuations. It would be much smoother. Because we don't have more ensemble members, more of these model runs with different initial conditions, what we do next is simply smooth out the red one and get the yellow one, and that's now our climate signal. So what the climate signal shows is that the climate warmed and then cooled and then warmed again. Regionally, in that place in the western US, even though the actual temperature over this period in the western US might have looked more like the black curve, which includes many ups and downs. So we can think about the red curve as being climate and the black curve, or the observed curve, as being the one realization of the climate system that does not by itself represent the effects of climate change only. While the red line indicates what are the effects of climate change specifically and only on the temperature in the West US. Make sense? We have to assume that this model actually correctly represents reality to believe that the average over these ensemble members gives us the correct effect of climate. So we're trusting the model in this case. And we have to do this for the attribution analysis. So now what we want to understand now is how to use these concepts, so the VPD and extracting climate change from climate variability using this ensemble average. We want to understand how to use this in order to calculate how much of the fires in the southwest US or the western US is due to climate change. So these are the steps. So let's outline these steps. So let's see. We have the record of the VPD and the area burned. Okay, we have these two records. We're going to try and do the regression writing log 10 of the area burned. We're going to write it as A times the VPD plus B. And we use regression in order to calculate A and B. So this is known, and this is known, and these two are unknown. So we use these two, we fit a line, and we find A and B. Here's what it looks like. This is this picture right here. So I'm plotting a scatter plot of the log of the area burned on the y-axis and the VPD for each year on the x-axis. You can see that they fall on a line, and I can calculate the slope of the line and the intersect, and that gives me A and B. So this is the relationship between the area burned, or the log 10 of the area burned, because we found that that gives us a better fit than just the area itself, versus the VPD. So that's how we calculate A and B, step number 1. So moving on. Now we go ahead and calculate the VPD, signal due to anthropogenic climate change. We do that by using this ensemble average that we just talked about. So ensemble average over data of model runs. Okay, so we do that. What does it look like? Let's look. What you see here is the record of the VPD versus here. And there are three curves. There's the observed VPD is the blue line. That's what this is. Okay, now you take these 30 model runs. You calculate, you plot the VPD for each of them, and then you average them together to get this dash line. So this dash line here is the equivalent of the yellow line we saw before for the temperature. What we're seeing here is the ACC contribution to the VPD. You can see that it's just a monotonic increase from 1985 to 2015. That's equivalent to the yellow line we saw before, while the blue line here, which is a single realization, the observed realization of the climate system, corresponds to this black line that we saw here, okay? So the black line could have been the observed signal. In this case, it's one of the model ensemble members. And this yellow line is the contribution to the ACC. You can see that if I plotted this from 1985 to 2015, it would look like a straight line, right? So that's what we see there for the VPD. So this is step number 2, is calculate the VPD due to anthropogenic climate change by using an ensemble model average, this thing here. Okay, step number 3. So let's call this VPD bar. VPD bar would be the contribution of climate change to the VPD as function of time. So now I can calculate area burnt due to ACC would be equal to, or log 10 of this area burned due to ACC would be equal to the A that I know, the VPD bar, plus B. So now I found the area burnt due to anthropogenic climate change. And then if I wanted the area burnt due to natural variability without climate change, so the area burnt due to natural variability alone, that would be the area burnt every year minus the area due to ACC. So that would be the contribution of natural variability alone. Let's look at that too. The area burnt is the red line here. Then we use the regression to calculate. We took this dash gray curve here, applied A and B to it, and calculated the area burnt due to climate change. And then we subtracted that from the red line. And then the gray line here is the area burnt due to natural variability according to this. That's the general idea of this analysis. So that can tell us, for example, what fraction of the area burnt in the western US over the last 10 years is due to climate change. We could do that analysis. We could also predict something, right? So, and you're going to do this now. You're going to ask now, okay, by how much VPD will increase in the future? You know that it depends on the temperature in a certain way. You know how VPD is related to the area burnt by calculating these A and B. And now you can calculate yourself by how much forest fires in the US would get stronger in the next 10, 20, 30 years based on these A and B that you'll be calculating. So you can now both attribute the forest fires that we've seen, and you can predict the forest fires in the next couple of decades. All of this, by the way, follows a very nice paper. And Williams was great help to me in understanding this whole thing. He was very generous with his time, I have to admit. So that was nice. I think we're ready for this one. Yeah, I think it would be best if we moved on now, with your permission. Possibly half or more of the area burnt of the last years is due to anthropogenic climate change. That's a remarkable result. And this correlation that we found between VPD and area is the basis of all that, right? The fact that these points lie on a line and that these two curves seem to fit each other very well is the basis for this analysis. Any questions about this? Okay, so it turns out that things are complicated as always. So now these are two scatter plots. In this case, you have log 10 of the area burnt versus VPD. We know that one. That's an impressive fit. And we use that to calculate an attribute and so on. This is another one. What's shown here is the percentage of wet days in a year versus the log 10 of the area. And that's also a good fit. So now the question is, which is the correct one? So you see, percentage of wet days makes sense. The higher the percentage of wet days, the less fires we expect, right? While it also makes sense that the higher the VPD, the more fires we have. The difference between these two predictors is how they behave from now until 2100, unfortunately. It turns out that the VPD, as we figured out, increases dramatically with temperature, while this percentage of wet days does not change dramatically in a future climate projection. This is based on this paper here. So if this is the correct reason for the change in the fire regime in the western US, then we expect further increase in the area as you're about to calculate, and these are going to be remarkable results, remarkably impressive numbers. If this is the correct one, then it means that we're not going to see a huge increase in forest area. And we don't know what is the fundamental reason for the increase in fires. Is it the change in wet days, or is it more like the change in VPD? Because we don't know that, There's an uncertainty in being able to project future expansion of fires. Make sense? So let's talk about the Australian fires now. That's a completely different example. As you'll see, so this was the Australian summer of 2019-20, and you can see pictures from these fires, obviously very dramatic. It's known as the Black Summer and had unusual intense fires in that area. Okay, so let's see. Let's look at this one.
Devastation in Australia, where thousands of firefighters and first...
Okay, you get the idea. So pretty unbelievably dramatic. And let's see, what does the press say about this? So Australia's angry summer. This is what climate change looks like. Of course, unusually hot summers have happened in the past. So had bad bushfire seasons, but the link between the current extremes and anthropogenic climate change is scientifically undisputable. That's what we're looking into to see whether it's scientifically undisputable. Climate drivers that cause to severe season and so on. So the angry summer playing out in Australia right now was predictable. The scientific evidence is well known for how anthropogenic greenhouse gas emissions are causing long-term climate change and forest fires. You get the idea, okay? Let's see what happened. So in the case of the western US, we concluded that 50% of the fires over the last decades was likely due to anthropogenic climate change. So I think we could call that undisputable. That's a pretty strong evidence. There is an uncertainty regarding future projections because of the question of what's important. Is it VPD or wet days? But that doesn't affect the attribution result, which is a big part of the forest fires was due to anthropogenic climate change likely. I mean, nothing is ever completely certain, but it seems pretty strong result. So let's see if that's the case also for Australia. So what affects Australian fires? This is a paper by King et al. 2020. And this is what La Nina is. Do people know about La Nina? When the sea surface temperature in the East Pacific becomes warmer by a few degrees, maybe 3-4 degrees more than the normal, this is referred to as El Nino. And while the sea surface temperature getting colder than normal, that would be a La Nina. El Ninos happen roughly every 2 to 7 years, and La Ninas happen between El Ninos. Okay. El Ninos and La Ninas are both close to Australia, so they affect the Australian temperatures, precipitation, and so on. There's another similar variability signal like that, which is referred to as the Indian Ocean Dipole. Here's what the Indian Ocean Dipole looks like. So if you take all of the cases where the Indian Ocean Dipole is positive and you average the sea surface temperature, you see such a dipole here where the West Indian Ocean is warm and the East is cold. And if you look at the negative Indian Ocean Dipole index, it would be exactly the opposite signal. See, this area is warm and this area is cold. And this clearly affects Australia, but also does El Nino and La Nina. So the precipitation in Australia, and therefore the droughts, and therefore the heat waves and so on, and therefore the forest fires all depend both on El Nino and the Indian Ocean Dipole, and on one more factor that we'll talk about in a second. But now that we know what El Nino and La Nina are, let's look at what do they say. So they say that the major Australian droughts of the past 100 years have coincided with several longer-term lasting events. Okay, so let's see. We need La Nina and Indian Ocean Dipole to be, so we need to have a La Nina and a negative Indian Ocean Dipole did not occur. So when these don't occur, there's a drought. Okay? Again, if La Nina doesn't occur and the negative Indian Ocean Dipole doesn't occur, then we tend to have long-lasting droughts. Okay. And there was a Second World War from 1935 to 45, which is the same thing. The La Nina and the Indian Ocean Dipole had favorable conditions for droughts. Okay, so these are natural variability modes. This isn't anthropogenic climate change. Both the Indian Ocean Dipole and the La Nina El Nino are natural variability modes. Of course, it's possible that El Ninos and the Indian Ocean Dipole would be affected by anthropogenic climate change. That's a possibility. We don't know whether we see that yet or not. That's a big uncertainty. Okay, here's what the East Indian Ocean looks like. You know, the cold and warm on the two sides of the Indian Ocean. We talked about that. And the third factor is something called the southern annular mode. So that's basically a you could look at it as a pattern of the sea level pressure that has some difference between the southern part of the southern hemisphere and the mid-latitude part, and that difference in sea level pressure or other related meteorological quantities is defined as an index of this southern annular mode. And turns out that this also affects droughts in Australia. So especially southeast Australia, where the fires were intense, is affected, the precipitation there is affected by three different natural variability modes: the southern annular mode, La Nina, and the Indian Ocean dipole. So now let's see what happened to these three variability modes and whether we could say whether these are to be blamed for that fire or maybe anthropogenic climate change. So here's a plot of these different factors. So the Indian Ocean dipole index, so we saw what positive and negative means, and you can see that it varies all over. And we're talking about this period right here, 2019, 2020. So this is Nino 3.4 is an index for El Nino. So when it's positive, it's an El Nino. When it's negative, it's a La Nina. You can clearly see that there wasn't an El Nino here because this is positive, and positive means El Nino rather than La Nina. The southern annular mode also has a complicated structure and variability all over the place. And this is the amount of rain, and you can see that this period had an unusually prolonged low precipitation. Okay? We need to analyze this a bit more. I'll show you in a second, but that's the idea. You look at the Indian Ocean dipole, you look at the Nino 3.4, which is the temperature in the East Pacific along the equator, and you look at this southern annular mode, which is the distribution of pressure in the southern hemisphere, atmospheric pressure in the southern hemisphere, and we try to find the correlation with rain. Is everyone clear on the complicated three natural variability modes? Okay. So we use a cluster analysis. What does this tell us? So we can now plot rain versus the Indian Ocean dipole, rain versus the Nino 3.4, and rain versus the southern annular mode. And we find a rainy year would be a blue square. See, a blue square is rainy year. So a blue square happens when the Indian Ocean dipole is not positive. Here's positive, and here's the Indian Ocean dipole, and this is a rainy year. It happens for roughly 0 IOD, lots of rain. The x-axis is rain. This one says that rainy year happens when there's a La Nina. The Nino 3.4 index is negative. And then finally, this shows that the rainy year happens when the southern annular mode is positive. Now let's see what happens during 2019, 2020. So for that, we're looking at this star. So the blue square is where a rainy year is, while the black star is what happens during 2019, 2020. So you see that in terms of IOD, the IOD was very high that time, even though a rainy year typically happens for an IOD of 0. So the IOD, the Indian Ocean dipole, the temperature in the Indian Ocean, was not consistent with the year of plenty of precipitation. So that would be one driver of a dry weather over Australia, the fact that the Indian Ocean sea surface temperature behaved like that. Then we look at El Nino, La Nina. So for a rainy year, we need to have a very negative signal here, so La Nina, but this was a weak El Nino, if anything. So 2019, 2020 did not have the right configuration of El Nino, La Nina for a rainy season. And finally, the southern annular mode should have been positive for a rainy year, but it's basically 0 during this period. So all three factors together combine to give us a year that is not rainy, and therefore there was such a low precipitation during 2019, 2020. So it's a combination of three different variability modes that affect precipitation over that part of Australia, and all of them combined to not give us a rainy year, and that led to the drought, and that drought led to the fires. And we didn't say anything about anthropogenic climate change because possibly it didn't play a role in this case. And again, there's a huge uncertainty in everything, but that's what the data seem to suggest. Any questions? Okay. So the bottom line here is that the Indian Ocean dipole, La Nina, and the southern annular mode all contributed to a dry year. Of course, in the future, when anthropogenic warming gets even stronger, that will become a big factor, including in Australia, and that might change the picture. But we're right now talking about one particular event in 2019, 2020 that we saw all these videos for, and we're trying to understand why that happened. And it seems like this may not necessarily be to an anthropogenic climate change, as opposed to what we saw for the western US, where there are strong indications that that did make the fires much stronger in that area. So there's no single simple answer for anything, as always. Okay, let's talk about global fires now. So this is the fire season length from some data set that people developed, and you can see that due to the warming, the fire season length is actually increasing in some areas. I think, Alexandra, I think you mentioned that that might happen, so it looks like the careful analysis shows that that indeed is the case. The area affected by a longer season of fire is getting larger, but the forest fires themselves go down, and it turns out that that is because of, not because of a climate effect, but because in Africa a huge amount of area was turned from savanna, where there used to be large fires, to agricultural land, and that changed the area being burned. So this isn't contradicting the idea that fires might increase or decrease. It simply is another anthropogenic effect that has nothing to do with climate. I think that's almost the end for today, so let me try to go through that. So we talked about being complicated. Let me remind you. We have two types of it's complicated today. Here's the first kind. This is the first reason things are complicated with fires. Basically, if I had to summarize this by one line, I would say there are other anthropogenic effects in addition to the anthropogenic climate change that might affect fire regimes, and therefore when we see a change to fire, it doesn't mean that it's because of climate change. It could be because of other human activities. That's one reason it's complicated. Now, here's the other reason it's complicated. So suppose we have an increased precipitation. Would that lead to more fires or less fires? Let's see. So if
there's more stuff to burn.
That's right. Yeah, you see, it's not intuitive necessarily, right? So if you have more precipitation, it depends. If the current climate is warm and you add precipitation, you can grow more vegetation, and then you'll have more fires. But if the current climate is moist and you have more precipitation, then the vegetation would be moister and you'll have less fire. Okay, so higher precipitation could either increase or decrease the amount of fires depending on the current regime. Clear? Okay. What happens if you have warmer and drier areas? So, okay. If we have areas rich with available fuels, so like the western US, that are vegetation rich, and you make the weather warmer and drier, then that will definitely increase fires. But if you have an area that is dry, and you make it even drier, there would be less vegetation and therefore less fires. So just like increased precipitation could increase or decrease fires, also warmer and drier weather could increase or decrease fires. Make sense? Nice. So it's not just temperature is increasing, more forest fires. That's a very narrow point of view dictated by what we have around us here. In other parts of the world, it could be very different. Okay, let's summarize it. So, bottom line, it's complicated. Fire is a natural process. It's very episodic. You have huge fires that could be very rare, like in Canada. Fires are very rare, but when they do happen, they're huge. So it's a very episodic process. Human effects include non-climate factors, which makes the attribution more complicated. And these non-climate factors include the fact that we start fires, we suppress fires. When we suppress fires, there's a fire deficit in the forest and fuel accumulation and so on. And the record is short. We don't have that many years with data about fires, so we can't check the correlations for a long enough time, so our correlations and regressions are a bit uncertain. And as we just discussed, different areas and different forest types and different climate regimes respond differently to warming and to changes in precipitation. So just from the fact that there's warming or cooling or increased precipitation or decreased precipitation, you can't conclude much about the change to the fire regime itself. Okay. So we seem to have found that West US fires did increase due to anthropogenic climate change. I'm comfortable with that attribution. I was dubious when I saw it the first time, but now that we've reproduced the analysis ourselves, it seems very convincing. That correlation between VPD and area burnt is very powerful. So I'm a believer. Australian fires seems to me that it's mostly natural variability, not necessarily anthropogenic climate change. We said that the global fires are decreasing due to land use changes in Africa. And we said that future projections, even though we can attribute the US fires to anthropogenic climate change, future projections are difficult because we don't know whether what's important is the VPD changes that are anticipated or the lack of change in the frequency of wet days, and we don't know which of these controls fires at present. So bottom line is that some changes are expected. So you see, even if you have a regime where there's going to be less fire, that's not necessarily good news, given that fire is part of the natural system. So if you have an area that adapted and evolved to deal with fires, and now there's less fires because of natural climate, because of anthropogenic climate change, that's not necessarily good news. Any change in this context is a change to an ecological system that has adapted to the current state over many, many years. So it's not a good idea to perturb it. And it looks like there are going to be changes, whether it's an increase or decrease in forest fires. Any final questions, anyone? All right. Great. See you next time.
Thank you.